Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll start the lecture 8B of this linear algebra chapter. So before starting this, basically like what will we cover in this lecture? So we'll cover the solution of homogeneous equations, then questions on homogeneous equations, and then also we cover a separate topic which is the LU decomposition. What do you mean by LU decomposition and how do we do it? And also we'll solve one example problem on it. So before going to this, I just wanted to give you a quick recap of what we learned in the previous lecture. So in the previous lecture, we learned about non-homogeneous equations and their solutions. What is nullity, what is free variables, all those things. So like it was a actually very long lecture. So first, like we already know this, that we did the valid matrix mapping, okay, and like where was it? I told you our rank also. Another method for finding rank. What was another method? Basically, the number of independent rows or columns. Okay, number of non-zero linearly independent rows or columns. So here I could see that either one of them will work, either independent columns or independent row, it doesn't matter, like both of them the number will be same only. Okay, I proved it to you here. So next we did few example problems, and like these are very important problems conceptually, so please do take a note of all this, right? So I told you, right, we have two types of systems of linear equation, homogeneous and non-homogeneous. For homogeneous, the constant part will be always 0, and for non-homogeneous, at least one of them has to be non-zero. Okay, simultaneously all of them cannot be 0. So this is homogeneous, this is non-homogeneous. So then I told you what type of solutions I can get from a linear system of linear equations. Basically I can get no solution. Basically they are not never crossing each other. I can get infinite or unique solution if they are always overlapping or they are only cutting at one point. Okay, then I did the matrix mapping. Basically I mapped the system of equations into matrix format. So we can form map in many ways, but generally we prefer this method instead of this method, right? So we prefer the column vector. This is also known as a column vector. Basically column matrix is known as a vector itself, so we prefer this method than this method. Okay, that's why you always see this one. Okay, but this is also valid. Now which are invalid? Basically these are invalid. Like you have to check, right, whether at the end I am getting the same equation from which I did the matrix mapping. That is very important, else this mapping will be invalid. So yeah, we did few questions, and then I told you what are the few cases for non-homogeneous equations. I will not go through this again. Basically if the determinant is non-zero, then you can confirm say that you will get a unique solution. Okay, because here determinant is only for one case, you are getting determinant non-zero, which is this case, right? This case. So it is a consistent set of solutions and you will get unique solutions. Now, if you found out the determinant of the coefficient matrix is 0, then you have to further check. You have to further check the ranks of both of them. So basically, determinant is 0, then it can be either no solution or it can be infinite solution. Now, if it is no solution, that means the rank of the augmented matrix and the rank of the coefficient matrix are both of them are same. And if it is infinitely many solutions, rank of the augmented matrix and rank of the coefficient matrix are lower than the number of variables, but they are equal. They are equal. Okay. Anyways, the determinant is 0, hence the rank of coefficient matrix will be less than the number of variables anyways. But if both of them are equal, then we'll get infinite solutions. So I just told you, right, how to identify each cases. Okay, then we did few questions and I solved this, right, for values of beta, what can happen for possibility cases, right? So then we learned about the free variables concept, nullity concept, all those things we learned about. I told you that there are two free variables here. Okay, two free variables, and these always contribute to null space, because if I put these values, right, I will always get a homogeneous equation, not a non-homogeneous. Basically the right hand side will be equal to 0 if I put these values, as I see, right? So here those things I told, so that's why studying homogeneous equation is also very important. So we did this question, and then I told you few things about nullity, and yeah, that's it, I think, like for this lecture. So let's start today's lecture. So today's lecture we'll learn about the homogeneous equations. So like A is a coefficient matrix that we already know, n cross n. So n is the number of variables. Now we have an augmented matrix, and the augmented matrix can be consistent. Okay, it can be consistent, like it is always consistent. There is no case of what do you say, no solution. There is no case of no solution, because it will always be consistent. Why? Because rank of A will always be equals to rank of B. Basically here what do you mean? So first of all, what is homogeneous equation? So homogeneous equation is basically Ax equals to 0. Ax equal to 0. Ax equal to 0. Now If A is equal to 0, then the right hand side is 0. The right hand column is totally 0. If it's totally 0, that means that obviously it won't matter. Okay, the rank of A will be same as rank of AB because the B is 0 itself. B is 0, right? So rank of A will always be equals to rank of AB, no matter what, because obviously B is 0, right? B is 0 matrix. Okay, so now if rank of A is equal to rank of AB, then what can happen? Then that unknown case can't happen, because sorry, not unknown, no solution case can't happen. For no solution, rank of A must not be equal to rank of AB. But here our rank of A is equal to rank of AB always. So only we'll get consistent solutions, and out of those consistent solutions, there are two possibilities. Either my rank of A is less than number of unknowns, then I will get infinite solutions. Okay, infinite solutions. And if my rank of A is equals to rank of AB, then I will get unique solution. Okay, two cases, infinite solution and unique solution. Okay, and this unique solution is also known as trivial solution, and is this infinite solution is also known as non-trivial solution. Why? I will tell you. So in this case, right, in this case, basically what is the main thing you have to keep in mind here, right? The determinant will be 0, because obviously rank of A is, just hold on a second, rank of A is less than the number of unknowns, so obviously it is not a full rank matrix, hence the determinant will be 0. That is basically why, because one row is at least one row will be dependent of other two rows or whatever. Okay, since there is dependency, obviously the determinant will go to 0. So this is 0. Now here, right, in this case, the determinant cannot go to 0, obviously, because it is equal to the number of unknowns. It is a full rank matrix. So if it is a full rank matrix, here determinant will not be equals to 0. Okay, so yeah, these are the two cases. Now what do I mean by trivial solution and non-trivial solution? So basically, if I have a question, do I have a question over here? Here, right, what is the most basic solution that we see? So also here you can see what is the most basic solution. Can you tell me a number, like, or a matrix at in place of x that I can put, and this will satisfy this equation for any value of a, for any value of a? If you like see this correctly, or like if you are able to understand this correctly, then you might say, sir, if I put a 0 as a column vector, right, or a column matrix of all zeros, column of all zeros, then this will be equal to 0 itself. So x equal to 0 is always a solution. X equal to 0 is always a solution of this equation, no matter what. That's why it is called a trivial solution. So here I'll put x equal to 0. Why trivial? Trivial because this is boring, right? We already know, like, before even doing anything, before even solving, before even knowing about A, we already know that x equal to 0 is a solution of this equation, always. So that's why this is a trivial solution, and that's why this is called a unique solution, because only x equal to 0 is a unique solution. For other cases, we'll always get infinite number of solutions, because rank will be less than rank of AB. If rank is equal to rank of AB, then it is unique solution, and that solution is trivial, x equal to 0. Okay, just hold on a second, let me check if everything is recording or not. Yeah, everything is recording, fine. So that is why it is called a trivial solution. Now what about the non-trivial solution? Like, non-trivial means it is not boring, because here have I written non-trivial? Yeah, I have written non-trivial. So basically we'll get infinite number of solutions, right? They are non-trivial because this is not boring, right? Because I'm getting one new solution, another new solution, and another new solution, infinitely many solutions. Okay, that's why this is non-repetitive, non-boring. That's why it is called non-trivial. Just I'm talking about the name, how you can remember the names, right? Sometimes students get confused with the names. That's why it is very important to take the analogy of the names. How did the names come up? So here trivial means boring, only zero solution. This is also called as zero solution. It is also called as zero solution. Zero solution. Okay, so yeah, now basically let's also, what is the main important point to note here? It will be always consistent. So I will write a homogeneous equation will always be consistent. A homogeneous equation will always be consistent. Okay, so this is one of the key points also here. So let's do a few questions and from there we'll understand this better, right? So here the first question is, for how many distinct values of k the system has infinite number of solutions? Okay, they are not asking about k, okay, they are asking about how many distinct values of k. Just remember this, what have they asked, what have they asked, very important in the examination hall also. Distinct values, right? They are not asking what is the value of k, they are asking how many distinct values of k the system has infinite number of solutions. Now when does a system has infinite number of solutions? A system has infinite number of solutions when we have what, we have non-trivial solutions, right? Okay, or the rank of a is less than the number of unknown variables, then we have infinite solutions, because unique solution is only one case where I have all zeros, and that is trivial solution. Infinite means many solutions. So that will happen if rank of a is less than number of unknowns, hence it is not a full rank matrix, hence the determinant is 0. So always you have to understand this, like go through the determinant case. So either the determinant will be 0 or non-zero, these two cases, right? And obviously first you check the homogeneity of the equation, whether the equation is homogeneous or not. Just hold on a second, let me make this camera. Why is this not camera not straight? I don't understand. Just hold on a second. Yeah, sorry for the thing. Okay, I'm trying to make it more straight. Yeah, so now let's start. Basically this is, first we'll check the homogeneity, and yes, this is a homogeneous equation because the right hand side is all zeros and the left hand side has only unknowns, no constants. So this is a homogeneous equation. Check 1, homogeneous equation. Now check 2 is, they are talking about what type of solution. They are talking about infinite number of solutions. So if it has infinite number of solutions, infinite, that means that determinant of a has to equal to 0. That is exactly what we'll do, right? So we'll just put this thing in here. So this will be k1 1 1 k1, and I'm just writing the coefficients 1 1 k. Okay, and the determinant of this is equals to 0. So simply what you can do, you can simply like add all this up, right, and then take it common. So if I add all this up and then take it common, what I'll get? So what I'm doing is, let me reduce the size of this. So what operation I will apply? I will apply I will change R1 to R1 plus R2 plus R3. So basically everything will be same only, okay, but one thing will change. So this will become k plus 2, all of this will be same only, k plus 2, k plus 2, k plus 2. Okay, so now what I can do, I can take k plus 2 common. Okay, I can take k plus 2 common, right? I can take common from any row or column. So this will become 1 1 1 1 k 1, and this like we have solved it multiple times, these type of things. So one value k equals to 2. So if k equals to 2, then this whole thing will become 0. So that is one valid value. So let us further solve this one. So this will become, basically this is 1 1 1. So this will become k minus 1, and this will be 0. Okay, k minus 1 and 0. So basically what will be the determinant? This is k plus 2 into this times this, and this is 0, right? So I will open about, okay, sorry, this also will go to 0, right? That is the main process of subtracting. So obviously I will open about this column. So only this minor will be left, right? And if this minor is left, so this is k minus 1 whole square equal to 0. So how many distinct values I have? I have k equals to minus 2, k equals to minus 2, k equals to 1 and 1. So number of distinct values for k is 2 because 1 is minus 2 and 1. So number of distinct values of k let's say whatever you name it, m or is equal to, okay, number of distinct is 2. So our answer will be 2 up here, right? This is our answer. Now let's go to the next question. So like this is the main concept of homogeneous equation. Just you have to understand the concept of determinant. Like will the determinant be equal to 0 or non-zero? What is the question trying to say to us, okay, about the determinants? So again, here the system of equations have non-trivial solutions, non-zero solutions, okay. Non-trivial solutions means infinite solutions. Again, the determinant we have to equate it with 0. But before that, obviously you check that whether this is a homogeneous equation or not. Yes, this is, because here on the left hand side I have all variables x, y, z, and on the right hand side I have zeros. So this is a homogeneous equation. So next they are asking then A, B, C are in. So A, B, C are in AP, GP, HP. So this we have already learned. Okay, sorry. This we have already learned in childhood, that whether they are in arithmetic progression, geometric progression, or harmonic progression, right? Harmonic progression. So yeah, let's basically try to solve this, okay, using the determinant, and then check the relationship between A, B, and C, and from there we'll understand which type of progression does it follow. So obviously I will again write the coefficient matrix, right? Coefficient matrix. One to A. This is 1, this is 1, 1, 1. This is 3B. This is 4C. This is B. This is C. Now this is equals to 0. Okay. So what can we do? We can't do much actually. So okay, basically what we can do, we can make this zeros, right? We already have 1. Previously we didn't have 1 in this column, but now we have. So we can make this column 0. So if we make this column 0, this will be 1, 0, 0, 2A, 3B minus 2A, B minus A, 4C minus 2A, C minus A. This is equals to 0, right? So now simply solving this, so only we'll have this minor left, right? All other things are 0 itself, because this is 0. I'm opening about the first column. So this will be 3B minus 2A into C minus A minus 4C minus 2A into B minus A into B minus A equals to 0. Now here I am not able to see anything, right? So what I will do, I will just expand this thing, expand the terms. So this will be 3BC minus 3AB and minus 2AC plus 2A square minus 4BC minus 4AC minus 2AB plus 2A square. So this is equals to, overall this is equals to 0. So if I write this in different, 3BC and this is 4BC, so overall this becomes minus BC. Don't take it otherwise, Bengalis. And this is minus 3AB and this is this becomes minus minus plus 2ab, so this is minus ab, fine, and this is minus 2ac, okay, and this is plus 4ac, so this becomes plus 2ac, and this is plus 2a square, and this is plus 2a square, and this is minus 2a square, so this becomes 0. So overall this is equals to 0. So what could be the answer? So answer is, if I divide by ABC on both sides, okay, then, and I take these two, right, negative signs 2 on the right hand side, this will become 2 by ABC. This is B only, B is left, and this is 1 by A plus 1 by B, 1 by C. Now, if you recall correctly, this is the relationship of harmonic progression of ABC. I should say A, B, C are in HP. Okay, A, B, C are in HP, harmonic progression. Okay, so this will be option C. Okay, nothing to like, nothing fancy over here. So what is this next question telling us? For what values of k, this should be actually value, okay, value of k, does the system of equations have two linearly independent solutions? For what value of k does the system has two linearly independent solutions? We have two linearly independent solutions. That means here, what is this first? What is this equation? System of equation. This is a homogeneous system of equations. So that is the first thing that you will notice. This is a homogeneous system of equation. Now, if it is a homogeneous system of equation, that means that for us to get two linearly independent solutions, the what? It has to have infinite solutions, right? Infinite solutions. That is the first thing. So obviously this is the case of infinite solution. That means the determinant of the coefficient matrix has to be equal to 0. Okay. So from that you can decode. Like if it was telling that only one solution it has, that is a 0 solution. So obviously determinant can't be equal to 0. So yeah, that you have to figure out. So for what value of k they are asking. So value of k we have to find out. So first thing is determinant of the coefficient matrix will be 0. So basically I've already written down the coefficient matrix and its determinant will be 0. So if I like rearrange this, I've already rearranged this. So basically this column, right, has 2 zeros and only 1 1. So simply if I open about this column, this is plus, this is minus, so hence this will, this doesn't matter, the minus sign anyways doesn't matter, but still minus 1 into k plus 1 into k square minus 1 minus 0 times k plus 1, so it is 0 itself, so this will be 0 itself, so this is equals to, okay, sorry, this is equals to 0. Now how can I write the k square minus 1? K square minus 1 I can write it as k minus 1 into k plus 1, so it will be k plus 1 whole square into k minus 1 equals to 0. K minus 1 equal to 0. Okay, so basically this will be k minus k equals to minus 1 and plus 1. Now in the options I am seeing that obviously both of them are present. Okay, so for k equals to minus 1 also I will get infinite number of solutions, and for k equals to plus 1 also I will get infinite number of solutions. But what does this mean? That the system of equations have two linearly independent solutions. What do you mean by that? So for us to understand that, we have to go much deeper in this. So I will write the coefficient matrix for two cases, for k equals to 1, k equals to minus 1, and from there we will understand. So here, tell me what is the rank of this coefficient matrix. The rank of this coefficient matrix is 2. Rank of this coefficient matrix is 2. So rank of this coefficient matrix is 2. Now if the rank of this coefficient matrix is 2, then what is the nullity? Nullity is simply number of 0 rows you can say, or total number of unknowns minus the rank. So total number of unknowns is 3 xyz, this is xyz, and rank is 2. So 3 minus 2 is 1. Okay, so nullity is equals to 1. Now basically we have one free variable. This represents one free variable, or from the 0 rows also we have only 1 0 row, so this also represents one free variable, right? One free variable. Okay, so basically now let us write the equations. So here if I write these two equations, right, so basically right hand side is 0 itself, augmented matrix, it is 0 itself, so I'm not writing the augmented matrix right now. So we'll just equate this with 0. So this is 2y plus 2z equals to 0, hence y plus z equals to 0. This is one equation. Then x plus y plus z equals to 0, and in the bottom right, if we have all zeros, so basically if you have all zeros, what I can say is I can take z as alpha. Okay, z as alpha I can take. Yeah, z as alpha I can take. If z is alpha, then y will be equals to minus alpha. Now if y is minus alpha, then x is equals to basically y plus z is 0 and so x is equals to 0 also. So it is 0 constant. Okay, it is not varying. So only y is dependent on z, and z is, we are free to choose z anything. Okay, we are free to choose z anything. So what is my solution vector? This is known as a vector. We'll understand more about vector later on. But for now, let's just understand that what is my solution vector. Solution vector is something like this: alpha times 0 minus 1 1. So my solution vector is only 1. Okay, I have only one solution vector. So I have only one solution vector here. One solution, right? One solution. Just write this in the bottom. One solution. So here they have told us two linearly independent solutions. So let's solve for the second case, and from there we'll understand what does it mean by two linearly independent solutions. So in the case 2, if I put k equals to minus 1, my coefficient matrix will become this. Now number of 0 rows is 2, so my nullity is 2, or rank is 1, and number of variables minus rank is 2. I can say it from the number of zeros as well, and from here as well, the formula as well. So nullity is 2, that means number of free variables is 2 free variables. Number of free variables will be 2. Anyways, you can see, right, 2 0 equation. So I have to like obviously choose y and z effectively, right? Or you can choose x also, it doesn't matter. So this equation is also saying 0 equals to 0, because right hand side I have anyway 0. I am not writing it over here. Right hand side is anyway 0, and this equation also saying 0 equals to 0. Two equations are saying. So basically I have to choose y equals to beta 1 and z equals to beta 2. Two free variables, right? So if I choose y equals to beta 1 and beta 2, so my x will be equals to basically x plus y plus z equals to 0 again, right? X will be equals to minus of beta 1 plus beta 2. Okay, now what is my solution vector? Okay, vector is anything, just a simple column matrix. Right now, for now, understand that vector is a simple column matrix. Okay, so my solution vector will look something like this, right? So total solution vector I am talking about, I've written it as x. Okay, this is actually the solution vector. Okay, just don't get confused with normal x. Okay, so everything is on, right? Yeah. So basically this I can write as this, that this is minus beta 1 plus beta 2. Then the y is what? Y is beta 1. So y is beta 1 and z is beta 2. Z is beta 2. Okay, so beta 1, beta 2. Now this will become, I can break this down, right? I can break this down in terms of beta 1 and beta 2. So if I write this as beta 1, this will be minus 1, this will be 1, and this will be 0, plus beta 2 and this is 1 minus 1 minus 1, and this is 0 and this is 1. Okay, now what do you observe? So either if you choose beta 2 equals to 0, I am free to choose beta 1 and beta 2. I am free to choose anything for beta 1 and beta 2. I am choosing beta 2 equals to 0. So my solution will be this, right? Infinitely solutions. Okay. Now if I choose beta 1 equals to 0, my solution will be this. Okay. So you pick, like you choose beta 2 equals to 1, right? Minus 1 and 1, you put this in the equation, you will get, yeah, it is validating the equations. So what I am seeing is these are two columns. Okay, are these linearly independent? Whenever I have two columns, right, I just have to check, are they proportional or not? If they are proportional, then obviously they will be linearly dependent. If they are not proportional, then obviously they will be linearly independent. So here, right, they are linearly independent because here I have 1, here I have 0. So I cannot never make this proportional, right? I can never make this proportional. Only if I multiply with this with 0, then this will be equal to this, but the other terms will be vanished. Okay, hence these two are linearly independent and these two are different solutions. Okay, so these two are linearly independent. Just hold on a second, everything is recording, right? Sometimes get tense. Yeah, everything is recording. Linearly independent. Okay, so these two are linearly independent. Exactly, that is what the question has asked us. The question has asked us that, can you tell me the value of k for which the system has two linearly independent solutions? So in the first value, right, I have only one, like one solution, right? And basically what I meant to say is, here obviously I have infinite number of solutions, that is true. For k equals to 1, I have infinite number of solutions, but only one type of solution. Okay, one type of solution. But in this case I have two types of solution, okay, which are linearly independent. But here, right, they are always linearly dependent, because the, let's say 0 minus 1 minus 0 minus 1 1, it is one solution for alpha equals to 1. Now if I put alpha equals to 2, it is 0 minus 2 2. Now is the current solution and the previous solution linearly dependent? They are, because simply they are just proportional to each other. They are just proportional to each other. So I will just choose here, just take one example, that alpha equals to 1. So if alpha equals to 1, then my solution is 0 minus 1 minus 1. And if my alpha is 2, let's say my alpha is 2, this is 0 minus 2 2. Okay, so are they linearly dependent? Yes, they are, because if I just multiply this with 2 and this will become this. So that is what the linear dependency means, right? Linear combination for the two columns or two row cases, it's just simply proportional to each other. So, yeah, so these are linearly dependent. These are linearly dependent. Linearly dependent. Now let's come to this case. Let's come to this case. So here, for beta equals to beta, let's take this case, that beta 1 equals to 1 and beta 2 equals to 0. Then my solution will be, I'm free to choose beta 1 and beta 2, anything, right? I'm free to choose that. So as these are free variables, so my x solution will be minus 1 1 0. Okay, and now if I choose beta 1 equals to 0, beta 2 equals to 1, then x equals to minus 1 0 1, right? So are these two linearly dependent or independent? I can never multiply a scalar with this and get this column, right? Never multiply a scalar and get this column. So these two are linearly dependent. Okay, so I hope you got the point. So in this case, the value of k equals to minus 1, I will get two linearly independent solutions. So the answer will be D. So yeah, this is a very good question on homogeneous equation, and these types of question may come later on, right, in the future. So yeah, this, just try to, if you couldn't grasp this concept, then try to again rewatch this, repeat this, and then I hope you will be able to understand, because I've broken this down into smaller bits, right? Everything I've broken down and explained very precisely and broadly. So let's solve this next question. So next question is basically, if the following matrix has a non-trivial solution, again non-zero solution, non-trivial solution, that means infinite solution, that means determinant of A is equal to 0. So for homogeneous, right, homogeneous, mostly determinant of A will be 0. Okay, that the question will always go to 0, but don't program your brain that always that will be the case. Someday it may happen that you have to solve it differently. Determinant of A will not be equal to 0, but mostly determinant of A equals to 0, that condition will come up in the case of homogeneous equations. Okay, so then which of the following option is true? Okay, so we have to check for which of the following option this is true, right? So basically determinant of A equal to 0, so I will write the coefficient matrix. If I write the coefficient matrix, I will directly make the determinant equal to 0. So the determinant is equal to 0. So basically this is PQ R Q RP RP Q, which is equals to 0, which is equals to 0, right? So now what can I do? So what I can observe is, if I add all these three columns, right, I will get P plus P, Q plus R. So I'll just do that, because anyways I can say this is 0 anyways, but that is fine. P plus Q plus R, P plus Q plus R, P plus, I will just write here. I'm not writing what operation I'm performing, because that will just waste your time. You know what operation I'm performing. Q R P R P Q equals to 0. Okay, so this equals to 0. Now either you can take this common, right, and you can say that P plus Q plus R must be equal to 0. Okay, like that is one case. Must, not must, it can be equal to 0. If it is equal to 0, then my determinant will be 0. So yeah, this option is satisfying, this option is satisfying. These two are gone. Okay, these two not possible. Let's come back to the next term. So here, so basically what you can say is, like just check the options. If P equals to minus Q equals to R, the determinant, can it be 0? P equals to minus Q, so this is minus Q and this is equals to P itself. So no, again, right, I'm not getting same rows. So okay, we can do it like differently also. Like let's solve it, or you can, like, basically the answer will be P equals to Q equals to R. So if you put here P equals to Q equals to R, this will be PPP, this will be PPP. So two columns are identical, then the determinant will go to 0. Okay, sure short. And P plus Q equals to P plus Q plus R equals to 0, that is also if that is 0, then obviously one complete column is 0, that means the determinant will be 0. So these two conditions are satisfying. From the options you can directly tick mark that this will be C. So you can solve by the options. Now if you don't want to solve by options, what you'll do, you'll take this P plus Q plus R common, right? Take this P plus Q plus R common. This will be 1 1 and 1. This will be QRP, QRP. This will be RPQ, RPQ. And this will be equal to 0. Hence this will be P plus Q plus R. Now I just simply, what I'll do, I will again make zeros, right? So I can make zeros directly here. This will be 0 itself. So I'm just subtracting the row 2 and row 3. Sorry, I'm subtracting row 1 from row 2 and row 3. So this will be R minus Q, and this will be P minus Q. So next what I'll do, I'll just simply write this in the determinant format. So this is R minus Q into Q minus P minus Q into P. Okay, so in this case, right, in this case, can I further break this down? R Q P Q Q square. No, I can't further break this down, right? So basically here, what do I observe? Okay, let me just break this down. P plus Q plus R into RQ minus Q square minus P square plus PQ. Okay, so this will be simply P plus Q plus R, this equals to 0, equals to if I take common Q, take common q, p plus r, and this will be minus p square and q square. Like anyways, minus p square q square. Yeah, these are 4 terms, right? So basically here, if p is equals to q, then this one is this is 2q square, and p is equals to q, this is also q, 2q. So this 2q square minus 2q square becomes 0. From here, if you put the values, you will get to see. Okay, or you can directly see from the columns itself. Okay, totally depends on you how you see. Okay, I showed you both of the methods. So basically now let's study this new topic, that is the LU decomposition. What do you mean by LU decomposition? So basically it is nothing, it is just a procedure method to find the solutions, right? To find the solutions. So we'll just go through this step by step, and you just have to understand the steps. You don't have to remember things. Okay, just by the analogy you will be able to understand everything. So what is LU? LU is lower upper decomposition. So I will say lower upper decomposition. LU, lower and upper. So lower comes first, then upper comes. And what is lower and upper? Lower means lower triangular matrix, and upper means upper triangular matrix. That is what the meaning of lower and upper is. And invertible matrix can be written as a product of a lower triangular and a upper triangular matrix if and only if its leading principal minors are non-zero. Okay, its leading principal minors are non-zero. Yeah, sorry, actually the light went off, that's why I paused the video. So I was talking about leading principal minors. So invertible matrix can be written as a product of lower triangular and upper triangular matrix if and only if its leading principal minors are non-zero. I talk about the leading principal minors. This is known as LU decomposition. Now in the question, if they have told you to solve using LU decomposition or something, and it can be only solved with LU decomposition, then obviously this condition will obviously be already valid. Okay, you don't have to check this condition in the examination hall. You don't have to waste your time. You can directly solve using LU decomposition. I'm just telling you when this is invalid. If one of the leading minors is 0, then this is invalid. Okay, so basically I have this equation, right? Non-homogeneous equation I have. Now before solving this, I want to tell you what does this principal minor means. Leading principal minors means. So the leading principal minor of order k, okay, k is 3 up here, is the minor of the order k obtained by deleting the last n minus k columns. Deleting the last n minus k columns. I think this should be written as order n. Okay, sorry, this is order k because this is talking about the minor itself. Order k, this is talking about the minor itself. So what does this statement means? So if I delete the, let's say I want to delete the last row and column. So it's talking, I have to delete both row and column because minor is a square matrix. So I have to do both, right? Same number of rows and columns should be same. So I delete both rows and columns. So if I delete the last row and column, what do I get? I get this, right? This m anything, right? m11, this is m11 is 5, 6, 8, 9. Okay, so this is the minor for m11, right? This element. So sorry, I made a mistake over. Sorry, not m11. Sorry. So this is the minor for the last one, m33. Basically, I am deleting the last row and the last column, right? Last column and the last row. So I will be left with only this. So 1, 2, 4, 5. Now, if I delete the last 2 columns and last 2 rows, then I will be only left with this one element, right? So another one is this one element only. Okay, and now if I don't delete anything, so it is talking about I have to delete the n minus k rows, right? So order is here, what is the order of the minor? 2 cross 2. So I have deleted 1 row and 1 column. That's why n minus k, 3 minus 1 is 2. The order is fine. Here how many rows and I have deleted how many rows and columns? I have deleted 2 rows and columns. So n minus 2, which is 3 minus 2, which is 1. So this is 1 cross 1. Now if I don't delete anything, 0. So n minus 0 will be 3. So order of my minor will be, let me not write this in numbers, this would be bad. So order of my minor will be m dash, m double dash, m triple dash is this whole matrix itself. So obviously if it is if it is invertible, then obviously this will be non-zero, right? So all of this should be not equals to 0. All of this should not be equals to 0, right? So then only you can say that we can convert it into LU decomposition. So this is very important point. Now let's how do we convert it into LU decomposition? So basically this is the simple equation that we know, right? Ax equal to b. So I just put the value of a here, x is here, and b is here. Now this a, right, this a can be broken down into a lower triangular matrix and a upper triangular matrix for that particular condition. Now what are the steps? First, generate a matrix A equals to LU such that L is a lower triangular matrix with principal diagonal elements equal to 1. So you have to remember this. You have to remember this, that first we write lower triangular matrix, then we write upper triangular matrix, and lower triangular matrix has one unique thing, that is the principal diagonal elements are all 1. Principal diagonal elements are all 1. Okay, so that is very important. Next is obviously it is a lower triangular matrix, so all the elements above the diagonal are 0. So here we are saying all the elements above the diagonal are 0. All the elements below the diagonal element are non-zero. So L21, L31, L32. Okay, they are non-zero. Now what is U? U is U11, U12, U13, U22, U23, U33. Now here the diagonal elements of them, there is no conditions specified to it. So it can be anything. It can be 1, it can be 2, anything, right? So just for lower triangular matrix, the diagonal elements are all 1. So for the upper triangular matrix, all the elements below the diagonal will be, principal diagonal will be 0. All the elements above will be non-zero. At least one of them has to be non-zero. Okay, so yeah, that is one thing. Next, we write A equals to LU. Now if you put A equals to LU in this equation, right, in this equation, if you put A equals to LU, what will you get? LU into x equals to b. Fine. Next, let ux equals to y. Y is another variable I am currently finding. U into x equals to y. Okay, just this ux I will replace with y. Y is a column vector itself, because this is what, let's say this is like this is 3 cross 1, right? 3 cross 3, 3 cross 3. So 3 cross 3 into this is 3 cross 1 column vector, where I have 3 rows and one column. So if I do 3 cross 3 into 3 cross 1, simply I will get 3 cross 1 back again. So this will be 3 cross 1 only. Okay, next what I'll write, Ly equals to b. So basically I am just replacing this ux with y in this equation 1. So if I replace this in equation 1, I will get Ly equals to b. So now I will find the values of L and y obviously from here. So basically I will write this equation, right? 1 times y1 into 0 times y2 into 0 times y3 equals to b1. So y1 will be equals to b1. Okay, so here I can simply do the matrix multiplication. Y1 will be equals to b1. Next I will go to the next row. L21 times y1, 1 times y2, 0 times y3. So L21 times y1, L21 times y1 plus 1 times y2 equals to b2. Now what do we know? We know y1 is equals to b1. So I can write y1 equals to b1. And the third equation, what do I get? I get L31 into y1, L33 into y2 into L33 into y2 plus y3 equals to b3. So from here you will be able to find out y1, y2 and y3, right? Okay, you will be able to find out y1, y2 and y3. Next what you will do, you will substitute the value of y in equation 2. Okay, in equation 2, in this equation you will substitute the value of y. Okay, and you will get the value of u as well. Okay, you will get the value of u as well, and by solving this we get x1, x1, x2, x3. Okay, this method is also called method of triangulation. So basically I think you couldn't understand anything, so obviously we'll do one example and from there we'll understand. So let's do this example. So solve the system of equations with using LU decomposition. Okay, so basically we have this system of equations, right? So first what we'll do, I will write the A, B matrix, all those things I will write, right? So what is my E matrix? Basically my equation is Ax equals to B, right? Ax equals to B. So what is my A matrix? A matrix is 1 minus 2 minus 5 1 1 1 3 1 3 1 minus 3, and this is x, y and z, right? X, y and z equals to B, which is 10 1 5. Okay, which is 10 1 5. So now basically what we'll do, we'll divide this into LU decomposition. So my A matrix, I can write this A matrix, let me take this to the next page, as a product of LU, right? So the diagonal elements will be 1, all ones. This will be L2 1, this will be L3 1, this will be L3 2, this will be 0, this will be 0, this will be 0. Okay, let me reduce the size. So what is this? This is U11, U12, U13, U22, U33, U23 and 0. Okay, I forgot to mention that, like in the step 1, right, in here, right here, if you write this LU equals to A, so from here you will get the values of L21 U11 and L21 and L23. Okay, so from here you will get the value. So I forgot to write here, from here. Okay, so from here you will get, so basically that is what we're doing. So yeah, now let us just simply do matrix multiplication. So first row times column, so 1 times U11 equals to what? This 1 itself. So 1 times U11 equals to 1. So my U11 is equals to 1. So what I will do, I will just keep on writing my upper triangular, like designing my upper triangular matrix and lower triangular matrix, because that will be really helpful to me. Okay, later on, because that will just not waste. So you can also do this in examination hall also. So U11 is 1, fine. Next, this row into this second column. So here in the second column, what I am getting U12, 1 times U12 into 0 times U22 into 0 times 0, which is 0, equals to this, right, second element. So this is minus 2. Okay, so U12 is minus 2. Now let's go to the third element. So third element is 1 times U13 and all this is 0 again. So U13 equals to minus 5. U13 is equals to minus 5. Okay, next is the second. Now I'll move on to the second row. So this is 1 times 1 plus 1 times L21 and 1 times L31 and L31, which is equals to what? Sorry, what I'm missing. Sorry, this I will multiply the second row and this column, right? So L21 into U11 and all these, right, will be 0. So L21 into U11 is equals to this element, which is 1. Now obviously U11 is itself 1, so L21 will also be equals to 1. So now I will start writing my lower triangular matrix as well. So the leading diagonal elements are all 1. Now this is L21 is equals to 1. This is 0, 0 and 0. Okay, so yeah, this is fine. Now let's go for the next equation. So here this second row into second column. So L21 into U12, 1 into U22 and everything else is 0. L21 into U12 plus 1 into U22. U22 equals to what? Equals to 1 over here, is equals to 1. So L21 is what? L21 is 1. So 1 times U12 is minus 2, I believe. Yeah, U12 is minus 2 plus U22 equals to 1. So my U22 equals to 3. So U22 is equals to 3. Now what about my other, right? So last like second row into last column. So L21 into U13 into U13 plus 1 into U23 plus this is 0, right? This is 0. So this equals 0. So basically L21 into U, what is U13? U13 is minus 5, I believe. Yeah, U13 is minus 5. So L21 into minus 5 plus u23. So L21 is what? L21 is 1, right? L21 is 1, so I will write 1 over here plus u23. I need to find the value of u23, so u23 will be equals to plus 5. Okay, so u23 is plus 5, second row, third column. Now this has been filled, so this will be 0 itself for triangular matrix. Just we need to find the last equation. So let us find the last equation, right? So this is just a time consuming thing, so basic calculation, so don't mess up with this calculation, right? That is very important. So let's go to the last row, here L31 into U11 equals to 3 itself. So L31 into U11 equals to 3. So L3 U11 is 1, so L31 will be equals to 3. So L31 will be equals to 3. Now let's go to the next. So this, right, L31 into U12 plus L32 into U22. L31 into U12 plus L32 into U22 equals to what? Equals to 1. So if it is equals to 1, what is this? This is L31 into U12. L31 is basically L31 is what? L31 is this. So L31, we have already found out the value of L31, which is 3. And what is U12? U12 is, I believe, minus 2, right? U12 is minus 2. So 3 into minus 2. That is why this is very time consuming actually. Now L32 we have to find out the value, and U22 we have already known, which is equals to 3. So this is equals to 3 equals to 1. So L32, this 6 will get there, so this will be 7, and L32 will be 7 by 3. Okay, now let's solve the last one. So here L31 into U13, L31, I'm just using different pen, L31 into U13, L31 into U13, L31 into U1, U13, then L32 into U23 plus L32 into U23, then 1 times U33, 1 times U33 equals to what? What is the last element? Last element is minus 3. So basically we've already found out what is L31. L31 is 3. What is U13? U13 is minus 5, I believe. Yeah, U13 is minus 5. So minus 5. Now what is L32? L32 is, which we have just found out, which is 7 by 3. What is U23? U23 is, we have just found out previously, which is equals to 5, right? Which is equals to 5. Was this equals to 0 really? Okay, I made a mistake over here. This, right? So this L21 into U13, L21 into U13, and then 1 into U23. This, right? This is equals to actually 1. This is not equals to 0. Sorry, my mistake. My bad. Not equal to 0. That is what happens, right? Some silly mistakes occur, creep up, and you make like huge errors. So sorry. So U23 is 1. So basically this will be 6, right? Times 6 plus U33 equals to minus 3. So basically what do you get? U33 value? U33 value equals to 214. So this is minus 15 plus 14 minus 1, and minus 1 goes on the other side. This becomes minus 2. So this is minus 2. U22 is minus 2. Sorry, U33 is minus 2, and L32 is 7 by 3. So this will be 7 by 3. Now next what you do, simply you write this, right? You basically write L times Y equals to B. By now we would have simply found out the solution of x, y, and z. Okay, but this is helpful in some other cases. That's why they do this. So the next step is Ly equals to B. Okay, so basically what is y? I should write y in capital actually. So y is actually u times x, right? U times x, which we'll find out later. So basically what is L? I will just directly copy L. and this is y1 y2 y3. And what is b matrix is this, right? B matrix is this 10 1 5. So this is 10 1 5. By now, if I would have done the inverse, I would have simply found out the solution, but that is fine. Okay, so sometimes they ask the L matrix or U matrix, then only it is useful. So from here you can simply find y1 equals to 10. Now y1 plus y2 equals to 1, hence y2 will be equals to minus 9. Okay, and 3y1 plus 7, this is 3 actually, should write, I am not writing it in hurry, this is 3. 7 by 3 into y2 plus y3 equals to 5. So basically 3y1 is 30 plus 7 by 3 into minus 9, which is minus 3, which is minus 21, plus y3 equals to 5. So this is 9 goes on that side, so this becomes minus 4. So y3 is equals to minus 4. Now basically what is this? Y equals to ux, so we will write that, right? So basically what is my u is this, right? So copy this. This is what this is 10 minus 9 and minus 4, right? So 10 minus 9 and minus 4. Okay, again the simple thing, right? So we'll start off from the last row this time. So if you start off from the last row, this is minus 2x3 equals to minus 4, right? So minus 2x3 equals to minus 4. So my x3 will be simply 2. Okay, now let's solve this equation. So this is 3x2 plus 5x3 equals to minus 10. So this is equals to 3x2, and this is my this is plus 2, right? So this is 10, and okay, am I doing something mistake? This is minus 9, right? Yeah, this is minus 9. Sorry. Yeah, this is 10. Yeah, this is minus 9. So this goes up there. So this goes to minus 19, and this is divided by 3. I'm making a mistake over here. I'm just checking. Just correct, right? 2 3 2 3. Just hold on a second, right? Okay, sorry. Actually, I just made a mistake over. I changed this to 6, but I forgotten to change this to 6. So that is what basically happens over here, right? So just be careful about this LU decomposition. You might make any mistake, right? So just be careful about this. This will be 6. That is what I was thinking, that what mistake I'm making. So this is actually 6. So this is 6. Hence this is 12. Hence this becomes minus 21. So x2 becomes minus 7. Okay, x2 is minus 7. And let's put all this in the first equation. So this is x1 minus 2x2 and x1, and this is minus 2x2. x2 is minus 7, x3 is 2. So x1 equals to 20, and this goes on that side. This is this is minus 10, and this is plus 14. So this is minus 4. This goes to that side. This becomes 14, right? So okay, wait. Sorry, this becomes plus 14, and this is minus 10. This becomes plus 4. If this goes to that side, this will become 6. So my solution x will be simply 6 minus 7 and 2. Okay, 6 minus 7 and 2. So this will be my answer to this question. So this is basically an example problem. Okay, and this is basically the end of this lecture. This was like a bit brief only. Basically, this LU decomposition, just you have to know the method, and sometimes they may ask the lower triangular matrix, sometimes they may ask the upper triangular matrix. Just you have to know the method, that's it. And that condition that I told about, you don't need to worry about it if they have already mentioned that LU decomposition is happening or something, because they have already done it, so obviously the condition will be valid anyways. So yeah, that's it for this lecture. Basically, I hope you learned, like, basically in the case of homogeneous equations, we will get either infinitely many solutions, or we'll get unique solution, that is basically the zero solution, x equal to 0. Okay, that is a trivial solution, and non-trivial solution are when I have infinite number of solutions. Now if I have infinite number of solutions, that means my rank of A will be less than the number of unknowns, so hence the determinant will always be 0. So most cases the question will come from determinant equal to 0, but you have to read the question, you have to understand the question, what they have asked. Sometimes it may happen that the condition may change, right? Condition may change, so you have to check the question. So that is the first thing. And I also told you the very interesting concept about the linearly independent solutions. So I hope you got the point, that when are my solutions linearly independent and when are they not. Okay, so anyways, the two for both of the values of k, I was getting infinitely many solutions. But which one I had to choose? I had to choose the k equals to -1, because there I was getting two linearly independent solutions. In the first case, I was getting linearly dependent solution. I was getting infinitely many solutions, but those were linearly dependent to each other. Okay, so yeah, that is the thing basically about this lecture. I hope you learned everything, and in the next lecture we'll start with eigenvalues and eigenvectors. So yeah, be prepared for that, and I will see you in the next lecture.